How many of you are familiar with Parkinson's disease? Heard of it? Okay. Perhaps you can think of a famous celebrity that has it. Canadian celebrity, Michael J. Fox. Okay. He's been living with it. It's a very debilitating disease. Right now, there's no cure for it. It's even very difficult to manage. But there was a woman, her name was Joy Milne, and she was actually given 12 pieces of clothing from 12 different people in order to see if she could smell Parkinson's disease or the onset of Parkinson's disease. And she got 11 out of 12 right, which was quite surprising. Okay, I mean, really lucky, or perhaps there's something there. Well, what we're going to do is we're going to look at that statistically, because what they did in China is they were so impressed with that they thought they would try and develop what was called an eNose that could detect Parkinson's disease. And if you can detect it early, perhaps you can treat it. Okay? So this is what we're going to look at, is this eNose based on this woman, Joy Milne. Okay? They tested it out. They came up with some results, and we want to check and see, is that statistically significant? Meaning, okay, was the result the eNose got so unusual that it couldn't be gotten by just being lucky, by chance alone? There must be some other explanation, and the other explanation is it must be able to do something. Okay? And that, again, that's what statistics is all about. So this eNose tested on 24 people, okay, the researchers. 12 had Parkinson's, 12 did not. So if the eNose doesn't work at all, let's assume we're in a world where the eNose doesn't work at all. How many guesses do you think it would get correct? Out of 24. Probably half, right? Kind of like flipping a coin. It's 50-50. I mean, you can either guess yes, guess no, and you got a 50% chance of being right. So probably 12. Probably 12. Because the probability of each guess would be 50%. You got a 50-50 chance. So you got a 50-50 chance every time. I mean, it may not be 12. Maybe it works out to 13 you got right, or 11 you got right, but probably somewhere 12 would be a good guess. Well, and this is just saying what proportion. So this is just changing it in to a mathematical value. So really, if we're going to say 12 out of 24, we're looking at a proportion of 0.5. Okay. And why? Same reason as above. You got a 50-50 chance of guessing correctly every time. It's got a 50-50 chance of guessing correctly each time. Okay, so they did it. They used this machine and it detected 17 out of 24. In Europe, we're 70.8% correct. So in your opinion, is this convincing evidence that this eNOS is probably more effective than randomly guessing. No? Nobody wants to venture a shot at it? Would you be convinced? I mean, what makes you think that, yeah, it could be effective? Yeah, it got 17 out of 24. But are you convinced? Not necessarily, because maybe this machine just got really lucky. We got to see if this amount guessed correctly out of 24, is that usual? Like, does that happen a fair amount? Or is that unusual? It very rarely happens. That will tell us whether it's convincing or not. Okay? So we would basically say it seems to be more effective. Because 70.8% correct. But I'm not convinced yet. So further study, statistical study, really, is needed. I don't think it's not good practice to simply say, oh, well, it got this once, so it must be more effective, and then stop there. We need more proof than this. We need to be more convinced than this. Okay? We need to know, like, what if we simulated this several times over? What would our results look like? So that's how we start. We do a simulation. So we're going to do this thing over and over and over again. We're going to assume that the chance of guessing correctly is 50%. And we want to see how unusual is it to guess 70.8% correctly. Okay? So when this was done several times over, these are the results we got. So you can see we got quite a few results, the majority where it was 50%. Next, a little less than 50, a little more than 50. Still a significant number that are over 40, but under 60. But as we go to either getting hardly any correct or getting most correct, that becomes very rare. Okay, so this is our sampling distribution, because remember, it's the proportion correct. Okay, so proportion, when we use the statistic for proportion in a sample, p hat. So, remember, it made correct guesses 17 out of 24 times, or 70.8%. So in a world where the machine was randomly guessing, meaning it would be 50%, is this result surprising? Looking at the distribution. Well, where is 70.8%? It's about here, right? A little past 70. It looks like only one result. We only got one time of, how many times did we do it? 30 trials. We tried it 30 times. And we got 70.8% or higher one time out of 30. So we got 70.8% one time out of 30. Or 1 out of 30, which is approximately 0.033 or 3.3%. That would be considered unusual because it rarely happens. Okay, 1 out of 30 times or 3.3% of the time. Usually we want 5% as a general guideline. If it happens under 5% of the time, it's unusual, which means it's surprising. Okay, so yes, it is surprising because it only happened 1 time out of 30 tries. When we did several samples, we got this distribution here and we graphed it. Does this shape look familiar to you? What does it look like? The normal curve. It's not perfect, but it's pretty close. Okay? And we like normal curves because we can do calculations with them if we know the mean and standard deviation. So yes, a normal curve. And remember, we can find the probability of something happening using a normal distribution as long as we know the mean and as long as we know the standard deviation. Well, there are ways to find these under a normal under certain conditions. Okay, I'll pull this out just to make sure I don't mess up the formulas. So under certain conditions, and most conditions we'll talk about next class or next week because we don't have class tomorrow. Okay. A sample proportion will follow a normal distribution. Let's see. The mean of the sample distribution will be the same as the population proportion. So if we were to average all those p's out above, we would get about 0.5. Well, that was the population proportion we started with, right? Because if it's just randomly guessing, it's a 50-50 chance. The standard deviation, and you'll get this formula always. Standard deviation of the sample distribution will be the square root of the population proportion times 1 minus the population proportion divided the sample size. We're not going to go into, it goes a little beyond this course, the actual explanations of these formulas, some of these formulas. Okay. Well, so let's look at this specific problem. All right, it's a sample, or it's a normal distribution. Why? Because we saw the shape of that on the graph. Well, in order to do normal calculations, we need to know the mean and the standard deviation. The mean of the sample distribution, notice how I say that. The mean of the sample distribution is the same as the mean of the the population proportion. What were the chances when it was random? 50. 50. It's also going to be that if we were to take several samples, or if we were to do it several times, average out all those proportions, it would average out to this. And then the standard deviation of the sampling distribution? Well, it's going to be the square root of p, which is 0.5, times 1 minus p, which is 1 minus 0.5, divided by n. What's n here? N is the sample size, 24. And then we just have to calculate that. So 0.5 times 0.5, divide 24, take the square root of it, go to 2 or 3 decimal places, really doesn't matter. I usually go to 3, okay? And you're going to get approximately 0.102. So it's a pretty small standard deviation. So now we can use this information to and the normal distribution and our graphing calculator to find what is the actual percentage of getting 70.8 or larger. Like by looking at this here, we think it's 1 out of 30, but there may be, I don't know if there's 30 in here. It's 29. Okay, so it's not like this isn't where they actually, it's somehow spread out in here. Okay, so it may be slightly different. So to do that, we got to use a normal curve. And with a normal curve comes a diagram. You want a horizontal axis, and your normal curve above it. And how many notches do we put in again? 7. Start in the middle for the mean, and then about halfway down the curve there, and then space them equally apart. You're about like that. Yeah.
What's like called in graphs, like switches directions?
Flexion points. And remember, you got a label. So really, this is p hat. So I'm just going to call it the sample proportion. I mean, if you want to go sample proportion of guesses, to do it in context, probably even better. But I think we'll be okay like this. And now we got to use those numbers we just calculated to put them in. So where does the mean go? In the middle. So we know that's 0.5. And then we got to add 0.102 3 times to the right. Subtract 0.102 3 times to the left. Right? So we're going to add a standard deviation. We get 0.602. We're going to add another 0.102. We're going to get 0.704. We're going to add another 0.102. We're going to get 0.806. I think those are right. Yeah. Then we're going to start at 0.5 and we're going to subtract 0.102. So we're going to get 0.398. Subtract 0.102 again, we're going to get 0.296. Subtract 0.102 the final time, we're going to get 0.194. Remember, we're looking for the probability of 70.8% or bigger. Well, here's 70.4%. So 70.8 is going to be just a little bit to the right of that notch. And I'm looking for the area of this region. Right there. So this is 0.708. I'm looking for that area. That tells me the probability of getting 70.8%. So using proper notation,
I'm trying to find the probability that, I'm not gonna just use X, is greater than or equal to 0.708. And how do I do it? I gotta do a normal calculation. Remember the function? Normal, what do we do on our graphing calculator? What's that one? Normal CDF. And then when you do that, you're going to get the lower boundary. You're going to have to be asked for the lower boundary, which in this case would be 0.708. You're going to be asked for the upper boundary, just go 1,000. So ridiculously big. The average we know is 0.5. And the standard deviation we know is 0.7, or sorry, 0.102. And then we do that on our calculator.
And remember, to do that on your calculator, you would do second bars because that represents distribution. Choose the normal distribution and then punch in your numbers, 0.708, 1,000, 0.5, 0.102, and we get we go 0.021. Now it's different than the 3.3 we got on the previous page, but remember that diagram on the previous page is not exactly the same as this. Okay, this is more precise. Because we didn't calculate the mean and standard deviation for this one up here. All we did was eyeball it. So just remember that. So are we convinced now? Yes. So because the chance of guessing correctly 70.8% or even more is so small, 2.1%. That makes it very unusual. And if something is unusual, that means it becomes convincing that it's effective. So we are convinced. We back it up with mathematics. The E-nose is more effective than guessing. This is how we're going to tackle all these problems for the remainder of the year. It's basically, we're going to get results, and we're going to look at those results, and we're going to ask ourselves, are those results really unusual? If they're not, then we don't have convincing evidence of some other claim. If it is really unusual, we have convincing evidence of some other claim. That's really what it comes down to. So just remember that as we do all these questions.
Okay.